share my screen. I'm probably muted as well. I hate the fact that I'm always come back muted every single time I come back and I'm like talking and no one can hear me. All right, at any rate, we are back. Let's take a look at what we've got. So here's an example, right? Heads or tails, and then 1, 2, 3, 4, 5, or 6 is your next option. Let's see if someone else had kind of the same thing. And then like here they wrote down, 1/6 for the dice, 1/2 for the heads or tails, which equals 1/12. And then these guys showed, you can also do it by looking at the sample space. So I'll show you that myself actually. So here is how it looks, right? And then if you kind of write the probabilities on the branch, you can do that as you want as well. This is how I suggest you do it. You do a probability tree. I want you to do it this way. Draw the branch and what goes at the end of the branch, right? This is my path to heads. Along the path to heads, the probability goes on the branch itself. Not here at the end, but right here. This is your, heads is your destination. So that's at the end, and then along the way you write the probabilities. So how to get from heads to 4, I'd go 1/2 times 1/6, and that would get me here. They're independent events, so you can just multiply their probabilities. Probability of head times probability of 4, 1/12. You can also use the sample space because they're all equally likely. So there's 12 items, 1 out of the 12 is the one that you want. Okay. Brenda, go ahead and read for me. Maybe Brenda can't read. Miriam, go ahead and read for me. It's hard for me to know who doesn't have a mic and who does. Okay, Danny. Oh, Danny, you must be. The odds that all 3 of you don't have mics is pretty unlikely. Can you guys see? Yeah, of course you guys can see. Okay, fine, I'll read. Trees are really helpful, especially when the probabilities are not the same. So, for example, I have 3 red marbles and 6 blue marbles. My first draw, I could draw a red marble or a blue marble. My second draw, since I'm putting it back, the probabilities would stay the same, red or blue. What's the probability I draw a red one? Guys, what's the probability I draw a red marble, the first one? I have 3 red marbles out of how many total? 9. Yep. So 3 out of 9. That reduces to 1/3. So I'm just going to do it like that. It's a little bit simpler. So 1/3 chance of red, 2/3 chance of blue. In general, I want you to not reduce. I kind of did a bad example here. It's better to not reduce them, ideally, and I'll show you why next class. Maybe this class, probably next class. So this is kind of a bad example for me to have done, but at any rate, I did reduce it here just for simplicity, so you can see the proportions and numbers that you're familiar with. And then, since I replaced it, for my second draw, it's going to be the same no matter what, the top or the bottom. These are going to be exactly the same because they're exactly the same as the first one. 1/3 chance of red, 2/3 chance of blue. 1/3 chance of red, 2/3 chance of blue. They're independent because I've replaced them. So you'll see, how do I get from one path to the next? So say red, red, 1/3 chance here, 1/3 chance there. You multiply along the branches. So 1/3 times 1/3 is 1/9. That's the probability of ending up right here at, that's supposed to be a red, sorry, that's wrong. It's an R. Uh-oh. Um, 1/3 chance of red, red. There's 1/3 times 1/3, 1/9 chance of red, red. 1/3 times 2/3, 2/9 chance of red then blue. 2/3 times 1/3, 2/9 chance of blue then red, and 2/3 times 2/3, 4/9 chance of blue, blue. Someone asked, how do you multiply fractions? You multiply the numerators So 2 times 2 is 4, and you multiply the denominators. 3 times 3 is 9. So that's how you get the denominator. You take the numerators, you just multiply across. So you just take the denominators and multiply across. That's how you multiply fractions. If you want, you can just put them in your calculator and give me a decimal. I'm okay with that. That's fine. That's not going to be, I'm going to be all right with that this semester. Another way of thinking of it, the way I like to think of it, is like this. So think of a river that's flowing. So here's this river that's flowing, and the river branches. A third of the river goes to red, and a third of the river goes to blue, right? So it branches off. I go along the one that goes towards red. So now I'm in this river, I'm floating around, now I'm bobbing along in my little raft, and it branches again. 1/3 to red, 2/3 to blue. And again, I take the red one. But it's not a third of the whole river, it's a third of the river, because I've already branched. So it's not the entire part, it's less. So here it's a third of the river, right? This is the whole river. This much of it, a third of it went towards red. And of that, only 1/3 of that went on to the second red. So it's really 1/9 of the entire river, a third of the river. Remember, of means multiply. So a third means multiply. A third times a third. Is nobody here?
You didn't end the Jamboards.
Oh, this totally sucks. Go ahead and work on problem 14 in your rooms. So I'll give you guys some time to do that. And again, if your group is kind of struggling and having trouble making the tree, and if you haven't kind of gotten anything done in the first couple, 2-3 minutes, I might send someone into your room. All right. This is something that's really interesting that you'll notice, is that this has to equal 1 or 100%. Because 100% of this river has to go somewhere. I can't have a third of the river go here and a half the river go there, and and then a little bit of it disappears into nothingness, right? All the river has to go somewhere. You also notice that of the part that goes here, 100% of that part has to go. This is a third of it, right? 100% of that third has to go somewhere else. So this has to add up to 1. This also has to add up to 1. The nifty thing you also notice is this also adds up to 1. Because this is after 2 branches, what fraction is in each branch. So if you look at it as a whole, that also adds up to 1. Did that answer your question?
Yeah. I mean, the first like 3, so you get the fraction basically from
3/9. Yeah, exactly. But I don't want you to reduce. So in your problem, do not reduce. I reduced just to make it simple for this example. In yours, leave the denominators alone, and I'll show you why later. You'll see next class when we start getting into more complicated things why it's easy to leave the denominators alone, because if you start reducing them, then they're not going to match up at the end. So when you want to add them later on, which we'll do later on, you're going to have trouble. So just what was that? Oh, 2.5 marbles? You can never have 2.5 marbles. No, you can't. I have 7 people. 2.5 of them can't choose. I have 12 puppies. 3.5 of them can't be yellow labs. So yeah, it's always going to be a whole number over a whole number. Yes, that's true. So if that's your question, the numerator is always going to be a whole number. The denominator is always going to be a whole number. Yeah, absolutely. Good question.
Professor Young?
Yes.
I don't have the link to the breakout rooms. I don't think.
Okay. I will text that to I will chat that to everybody now, if you don't have it. And I'm gonna.
No, I think she's saying we're not in breakout.
Oh yeah.
We didn't get the note.
Yeah. No, you are now.
Thank you.
I was trying to show you guys a couple things before you guys left. Okay, so we are back. Thank you so much. Well, let me know, you guys, if you can, because Apparently I take forever to learn this. Alright, so we have 3 red marbles, 1 green marble, 6 blue marbles in a bag. Draw a marble, replace it, draw again. Make a tree and find the following probabilities. So here's a very, very nice tree, right? You could draw a green, a red, a green, or a blue. 3 out of 10 are red, 1 out of 10 is green, 6 out of 10 are blue. Then, if you drew a red one, again, you draw a second one. You could draw a red, a green, or blue. And no matter what, since it's independent, because you placed it, the probabilities remain the same. So everyone's pretty good about this first one. The probability of drawing a red on the first one is 3 out of 10. Now, let me show you. Here are my marbles. They're actually, oops, okay. Let me grab my thing. All right. What's the probability that okay, so I'm going to draw one. I'll draw one. And then I'm going to put it back. Now, for my second draw, what's the probability I do not draw a red one? How many are red? What's the probability I do draw a red one?
Like 3 out of 10.
3 out of 10, same. What's the probability I don't draw a red one?
7 out of 10.
7 out of 10. 1 minus that, right? Because they're complements. So I have to add that 3 out of 10 I do, 7 out of 10 I don't. So that would be 7 out of 10. And then the last one is red then blue. So this is good. I like this one. So here we go red, so we go along this path, and then we go blue along this path, which means that we're going to multiply these 2 numbers here. Right, we're gonna do 3 over 10 times 6 over 10, and you'll end up with 3 times 6 is 18. Again, you multiply the numerators and you multiply the denominators. So 3 times 6 is 18. 10 times 10 is 100. If you really want to know more about multiplying fractions, I have some interesting different, videos and things like that from the algebra classes I can show you, but I don't want to spend time here doing that. Okay, great. So nicely done. Now I want to talk a little bit about what do we do when the population's really, really big. So, for example, all Americans, right, or all Californians even. How many Americans are there in the world? Anyone? How many Americans are there?
Probably 300 million.
A lot, exactly. There's tons, right? Everyone's on board with that one. There's a lot of them. I can probably delete this. Why is it? There we go. All right. So say there's 350 million Americans. That's a lot. If I sample and take and don't replace 10 people from this group, or even 100, is that going to make a big difference as 350 million people? What percent is 100 people? 100 people out of 350 million. I don't know. Hey Google, what's 100 divided by 350 million? Clearly it can't hear me. Where's my phone? Oh dear. Hey Google.
Can I guess? 35,000? I think we just take off the 2 zeros, because that's what I learned.
Yeah. So it'd be 1 over 35 million. No, or 3.5 million.
Yeah.
Right? So it ends up being something really, really small. 1 divided by 3.5 million.
It's going to come out to, what, 2.85, 71, 42.
Yeah.
Negative 7.
Right. So we'll talk about that in a second. So it ends up giving you this, 2.857 E -7. This E -7, you can't ignore it. What it means is it's gonna be a number. It's gonna be really small or really big. -7. Really small. Yep. So you're gonna draw 7. This is one of my students' best shortcuts. You draw 7 zeros, and your decimal place goes after the first 0. Oops, that wasn't a very good decimal place. After the first 0. And then you write the rest of the number in, 25285. That's how much it. So do you really think that this makes any difference at all in your probability? 46%. That's 0.46 compared to changing it that much. That's not going to have any effect at all. It's still going to be 46%. Do you guys understand what I'm saying? It's still going to be 46.000% even. So grabbing 100 people even out of all Americans, or even out of all Californians, makes really no difference whatsoever in this. So that's why this 46% doesn't, it's like replacement. It doesn't change because the population is very large compared to what you're grabbing. If the fraction of what you're grabbing is less than 1/10 of 1%, that makes no difference whatsoever. Okay. All right, so that's why that doesn't change. The 46% doesn't change. So here's my question next. What's the probability? It says, let's get a reader. Jalen, go ahead and read for me.
Selected at random. Find the probability that all three will say that they suffer great stress at least once a week.
Great. So if I randomly pick an American, what's the probability that they suffer great stress at least once a week? If I randomly choose an American, what percent of Americans suffer great stress, guys?
46.
46%. So if I randomly pick somebody, what's the probability that they suffer great stress? 46%. So I grab Sky. What's the probability that Sky suffers great stress at least once a week? It's not a trick question. 46%, exactly. Then I grab Guru. What's the probability that Guru suffers great stress at least once a week? 46%, exactly. And then I grab David. What's the probability that David suffers great stress at least once a week? 46%. Now, here's the thing. I want a probability that Sky does, and who's the person I picked? Elizabeth does, and Guru does. All three of them suffer great stress at least once a week. So that means that this person and this person and this person, and we multiply. Great. And we multiply. So we're going to multiply the probabilities, and we will get 0.46 times 0.46 times 0.46, 0.097. Good? Making sense for folks? You could draw a tree if you wanted to. You don't need to, but you would end up, it looks something like, if I were, it'd be like this. Stress, no stress, 0.46. Stress, no stress. Stress, no stress. We only care about this pathway here. And this pathway here is 0.46 times 0.46 times 0.46. That's all we care about, is that pathway. That all three of them do yes and yes, stress and stress and stress. And that was where we get the 0.097. Is that unusual? Is 0.097% or 0.097 unusual? 9.7%? What's our guideline for unusual again, guys? Unusual.
5%. 5%?
5% or less. Right, 5% or less is unusual. If something is 5% or less likely to happen, it's unusual. Is this unusual?
No.
No, it's not. It's more than 5%. It's not unusual. And again, remember, to get from cents, between percent and decimals to percent, this is like, just look at the cents part, and the cents symbol is 9, so this is like 9 cents. Do you guys understand what I'm saying? 9 cents, and then ignore what comes after it. 9 cents, so I'd write it as 9%, and then just add the decimal place for whatever comes after it, if that makes kind of any sense. It's really 9%, 9 cents, because this is the 9 is in the cents position. Okay, so what I want you guys to do is lab problem 15 on your worksheet. I'm only going to give you guys 3 minutes to do this. So hop in quickly, hop back out, and we will resume. All right, great job. You guys are back. Well done, you guys all have this one. It's 0.21 to the 4th power, or 0.21 times itself 4 times, so 0.0019. Yes, it's very unlikely because it is less than 5%. Absolutely. Good. So you guys all totally got all this. Nice job. Great. Now, we are going to, we're going to skip ahead a little bit. We'll come back to this in a minute, 16 in a minute, or skip ahead a couple pages. I want to jump into talking about complementary events again. So let me get someone to read this. Nicolette, let me just get you to read it. You're here. Oops, sorry. Hold on. Go ahead and read it.
Remember complementary events. The complementary event of E, denoted by E bar, is a set of outcomes in the sample space that are not included in the outcomes of the event E. Is everything that is not E.
Right, everything that's not E. So the nice thing is, right, remember we did this one last class, we talked about, you know, chocolate, probably someone's favorite flavor is chocolate, and probably the favorite flavor is not chocolate. Those have to add up to 1 or 100%. So that's kind of the nice thing. We're going to jump down to the bottom of page 15. That's where we are. Complement rule. We're just reminding you that. So complement rule, probability of A is equal to, I'll just write it in here. Actually, I'll hang on. I'll write it in here. This is kind of messed up. Annotate. Minus. That's supposed to be a minus. Minus. I got the wrong color on. Black. Minus. 1 minus the probability of A complement. So complement rule, bottom of page 15, you'll be writing probability of A is equal to 1 minus the probability of A complement, or A bar. You could do either one. The other thing you're going to note is that, so this is just a variation on the previous slide, right? The previous slide talked about, if you add them up, you get 1, which means that if you 1 minus the probability of the complement gives you probability of E, right? Because all we do is if you subtract probability of E complement from both sides, you get, that's how you get back and forth between these two. All we do is substitute A in for E. Probability of A is equal to 1 minus probability of A bar, or A complement. So where that comes in for us is either I have at least one sibling, or I have what? Guys, either I have at least one sibling, or I have, either you have at least one sibling, or you have, fill in the blank. What is it?
0?
Yeah, none. You have no siblings. Either you have at least one, or you have none. Does everybody agree? Those are your only options. So those are complements, because you're either going to have one or the other. So at least one and none are complements. We're going to make full use of that fact. These two are complements, so that at least one is the same thing as, the probability of at least one is the same as 1 minus the probability of none. So, here, I'll type it out. Probability of at least one equals 1 minus the probability of none. And that is in your notes as well, at the bottom of page 15. So, for example, probability of rolling 3 dice and getting at least 1 4. It's hard to find at least 1 4. I'll show you why in a minute. Instead, it's easier to find the probability of no 4s and subtract that from 1. That's much simpler. And this is what it is. I'll show you how we get that in a second. So the first question is, what's the probability of at least 1, 4, and 3 rolls of dice? I roll the dice 3 times. I have my big giant dice. I'm going to roll it 3 times. How many 4s could I get?
3.
3, or?
None.
None, or? Those are good options. I could get 3. Yep, I could get 3.
2.
I could get 2, 1, or 0. Those are all the options, right? Which of these are at least 1?
1 through 3.
Yep, 1 through 3. Good. Nice. Not a trick question. Good. All right, so I could find the probability of 1 plus the probability of 2 4s plus the probability of 3 4s and add all those up. Or I just find the probability of no 4s and subtract that from 1. Let's try listing them out. How many ways can you get 1 4? I'll give you a hint. So 1 4, 3 dice. I'm rolling dice 3 times. I could get 4, then not. That's one way. What's another way of getting 1 4?
Not 4, not.
Not 4, not. Someone else, what's the last way of getting 1 4? Exactly 1 4.
Not 4.
Not 4. Well done. Now, how many ways can I get 2 4s?
4, 4, 9.
4 4, not. Great. Someone else, a different way?
4,
not 4.
4, not 4. And last way? Anyone?
Not 4, 4.
Not 4 4. Exactly. Good. How many ways are there getting 3 4s? That's easy. 4 4 4. There's only one way to do that one. The all and the none, there's only one way, so it's a lot simpler. So I could, I'm going to undo all these now that we've kind of done them. Oops. So I could find all of these, right? And I want these ones here. I can find all 7 of these and add them up. Or I could just find this one guy and subtract it from 1. That's a lot easier. Do you guys understand what I'm saying? I can calculate all 7 of these and add them up, or just find this one path and subtract it from 1. It's way, way simpler. So that's what we did. Right? You don't even need a tree. So there's only one way of getting no 4s. Right? How many ways are there? It's just this one pathway here. That's all there is. So I could just do this and say, just this one pathway. That's all I care about. And there is a 1/6 chance of getting a 4, so that means there's a 5/6 chance of not getting a 4. Since this spot here, there's also a 5/6 chance of not getting a 4 there. And the third roll, there's a 5/6 chance of not getting a 4 there. So I see if find this one pathway. It's just like the one you guys just did a second ago. 5/6 times 5/6 times 5/6. You can do it as a decimal. I don't need the fraction. If you gave me a decimal, that's totally acceptable. I'm absolutely okay with that.
Could you explain really quick where you got 5/6 from again?
Yeah. What's the probability of getting a 4? I have a dice. What's probably I roll a 4?
1 out of 6.
1 out of 6. What's probably I don't?
5 out of 6.
Exactly.
Ah, I gotcha.
Yeah.
Thank you.
Yeah, you're welcome. Thanks for asking the questions. Okay, so we are here. Right, so again, I don't even need a tree since it's only one way of getting no 4s. Right, you guys just did it a second ago. What's the probability of 3 people, 4 people, all, what was it, buying ties, whatever it was. You did 0.21 to the 4th power. This would be 5, 6 to the 3 dice, 3rd power. So 5, 6 to the 3rd power. That's the this right here is the probability of no 4s, right? So I do 1 minus that, and I get the right answer. If you gave it to me as a decimal place, I'm totally okay with that. I don't need a fraction. I just like to work in fractions wherever I do because it's cleaner, and so I like it better. You guys now have one to do of your own. You have Lab 19. So I'm going to pop you guys into your groups. Hop in there. And, okay, before I do that, let me explain to you what's going on. So, let's get a reader. Colleen, go ahead and read for me. Or Serena, you haven't read yet. Serena, read for me.
The Neckwear Association of America reported that 3% of ties sold in the United States are bow ties. If 4 customers who purchase the tie are randomly selected, find the probability that at least one purchase of bow tie.
Right. So I pick somebody. Elizabeth walks into the shop. What's probably that Elizabeth buys a bow tie from me? 3%. Great. What's probably she doesn't buy a bow tie?
97.
97%. 97 cents. 0.97. Right. So 0.97 chance she does not. 0.03 chance she does. Okay, then Olivia walks in. What's probably that Olivia buys a bow tie?
3%.
3%. What's probably she doesn't?
97.
97%. Grace walks in. What's probably Grace buys a bow tie? 3%. Probably she doesn't. 97%. And then Gavin walks in. What's probably Gavin buys a bow tie? Again, 3%. Probably he doesn't. 97%. So I want to find the probability that at least one purchases a bow tie, which means I want to find the probability that none of them buy the bow tie. All right. 3 minutes, maybe less. Hop in your rooms and find that. And then we'll come back.